In the last presentation, we kept input voltage and load resistance fixed. In this lecture, input voltage is fixed but load resistance is variable. This is the symbol for varying load, and when load resistance is too small, voltage across the Zener diode will be smaller than Vz, Zener voltage, and it will remain off. For example, when load resistance is equal to 0, Zener diode will be short circuited like this, and voltage across Zener diode is equal to 0. VTH is equal to 0 in this case, and it is smaller than Vz, so the diode will remain off. So we need to find out minimum load resistance that will turn on the diode, and after this we will find out the condition for maximum load resistance. So there are two things in this lecture. First thing is to find out condition for minimum load resistance, and the second thing is to find out condition for maximum load resistance, because load resistance is varying. Vi is the input voltage, R is the current limiting resistance, and the voltage across the R is VR. RL is the varying load, and voltage across RL is VL. Vz is the Zener potential or Zener voltage. PZM is the maximum power dissipation capability of the Zener diode. Let's say current in this branch is IR, current in this branch is IL, and current in this branch is IZ. IZ is the Zener current, and we have to find out condition for minimum load resistance. Condition for minimum load resistance RL. This is what we have to find. And when load resistance is minimum, voltage across Zener diode is equal to Vz, because this is the boundary condition and we want to turn on Zener diode. It will turn on when voltage across the Zener diode is equal to Vz, and this is the condition when the load resistance is minimum. Voltage across the Zener diode is equal to VTH. We can calculate it by using the Thevenin's theorem, and it is equal to VI RL divided by R plus RL. This is the voltage across the Zener diode, and it is equal to Vz. Vz is equal to VL. Vz is equal to VL. This is what we have in this condition, and we can easily calculate the value of RL, and RL will be the minimum value for the load resistance. So let's try to find out value for RL. We have VI multiplied by RL divided by R plus RL. I will multiply both the sides by R plus RL. So we have Vz in bracket R plus RL equals to VI RL. Now I will open this bracket. We have VZR plus VZRL equal to VI RL. So RL is simply equal to Vz multiplied by R divided by Vi minus Vz. This is what we have after the simplification, and this is the condition. This is the condition for minimum load resistance. I will call this RL minimum. This is RL minimum. Now when load resistance is minimum, current through the load will be maximum. When load resistance is minimum, current flowing through this load will be maximum. So in this case IL is maximum, and it is equal to VL divided by RL minimum. VL is equal to Vz, so we have Vz divided by RL minimum. This is the formula for IL maximum, the maximum value of load current. If we apply Kirchhoff's current law at this node, then we have IR equal to IZ plus IL. When IL is maximum, IZ will be minimum. Well, IL is maximum, IZ will be minimum. So we have minimum Zener current in this condition, and we can easily calculate it. Iz minimum is equal to IR minus IL maximum. We can easily calculate the value of IL maximum from this formula, and IR is simply equal to Vi minus Vz divided by R. This is the value of IR. So we can easily calculate the minimum Zener current. This is all for the first condition. Now we will move to the second condition, in which we will try to find out condition for maximum load resistance. Condition for maximum load resistance RL. When load resistance is maximum, this implies load current is minimum, and when load current is minimum, this implies Zener current is maximum. Now what is the condition for Zener current to be maximum? We already know PZM is the maximum power dissipation capability of the diode, and it is equal to Iz maximum multiplied by Vz. Vz is the fixed value, and to have the maximum power dissipation, Iz must be maximum. So this is the condition for Iz to be maximum, and we can easily calculate Iz maximum by dividing PZM by Vz. These two values will always be given in the problem, so we can calculate Iz maximum, and from this formula we can calculate IL minimum is equal to IR minus Iz maximum. Iz maximum is equal to this, and IR is Vi minus Vz divided by R, and Iz maximum is equal to PZM divided by Vz. In this way we can calculate IL minimum. Now we have IL minimum, and by using this we can calculate the maximum value for load resistance. RL maximum is equal to VL divided by IL minimum. VL is equal to Vz, so we have Vz divided by IL minimum. So this is the condition for maximum load resistance, and by using these two conditions we can easily solve numerical problems. I will solve one numerical problem so that we can practice what we have learned till now. In this example we have to determine maximum and minimum values of load resistance. This is the given circuit. In this circuit, R is equal to 222 ohms. R is the current limiting resistance. Vi is equal to 20 volts. You can see Vz is equal to 10 volts. PZM is equal to 400 milliwatts. These are the given values, and we have to calculate minimum and maximum values of load resistance. This current is IR, this current is IL, load current, and this current here is Iz, Zener current. First I will calculate the minimum load resistance RL minimum, and it is equal to Vz multiplied by R divided by Vi minus Vz. I am directly using the formula that we have derived. Here you can see the formula for RL minimum. Vz is equal to 10 volts, so we have 10 multiplied by 222, the value of R, divided by 20 minus 10, and when you solve this you have 222 ohms as the value of RL minimum. I will also calculate IL maximum, because when load resistance is minimum, the current through the load is maximum, and it is equal to Vz divided by RL minimum. Vz is 10 volts, RL minimum is 222 ohms, so we have 45 milliamps as the value of IL maximum. This is the maximum current that can flow through the load resistance. Now we will move to the second part, in which we will calculate the maximum value of load resistance. In order to calculate the maximum value of load resistance, I will use the value of PZM. PZM is equal to 400 milliwatts. PZM is equal to Iz maximum multiplied by Vz. and it is equal to 400 milliwatts. Vz is equal to 10 volts, so Iz max is simply equal to 40 milliamps. This is the value for maximum Zener current, and I will use this value to obtain IL minimum load current, and this is equal to 45 milliamps minus 40 milliamps. 45 milliamps is the value of IR. IR is equal to Vi minus Vz divided by R. You can calculate it and it will be equal to 45 milliamps. So IL minimum is equal to 5 milliamps. Now we can easily calculate RL maximum, the maximum value of load current, and this is equal to Vz divided by 5 milliamps. Vz is 10. 10 divided by 5 milliamps is equal to 2 kilo ohms. 2 kilo ohms. This is the answer. This is all for this lecture. I hope you now know how to deal with the varying resistance and fixed input voltage. If you have any doubt, you may ask in the comment section. I will end this lecture here. See you in the next one.